In this lab, our goal will be to find the mass of a black hole using an orbiting star's motion data and appropriate physics principles. Instead of predicting the motion of the system using the net force, as we did in the first two labs, this time we will have to use the motion data for the system to predict the net force in order to find the black hole's mass. The result was that I found the black hole's mass to be equal to 2.388 times 10 to the 31st kilograms. Next, I will show you how I came up with this. Here are some of the physics principles I used in this lab. First, the momentum principle states that the total net force is equal to the change in momentum over the change in time, which is relatively equal to dp over dt when delta t is small. Also, we know that the sum of the parallel and perpendicular components of dp dt are equal to dp dt. The parallel component of dp dt is the product of d magnitude of p over dt times p hat. Since we know that in this case F net will be equal to the force of the gravity on the star by the black hole, we can use the law of universal gravitation to find the mass of the black hole. Here are our initial conditions. The system will be the star. The total net force will be due to the force of gravity on the star by the black hole. The black hole will be located at this unchanging position. The star's mass is 1.989 times 10 to the 27th kilogram. Delta t will be 86,400 seconds. Lastly, the x and y components of the star's position data were given in the CSV file. Next, I input these initial conditions into Python, such as the star's mass, the black hole's position, and delta t. In the first calculation loop, I specified the y component of the velocity to be equal to the final position minus the initial condition divided by delta t. Combining the x and y components of the velocity gives us the velocity vectors, both v initial and v final. To find p initial and final, I just multiplied the star's mass by v initial and v final. I set both delta v and delta p equal to the final minus initial calculations, and dp dt is relatively equal to delta p over delta t, since delta t is relatively small compared to the duration of the motion. Here is where we use the momentum principle to state that F net equals dp dt. Next, to calculate the parallel component of dp dt, we find the unit vector of the momentum to be equal to the momentum divided by its magnitude. Multiplying this by the d magnitude of p dt will give us the parallel component of dp dt. Using Newton's second law again, we can say that F net parallel is equal to dp dt parallel. To find the perpendicular component, we just subtract the parallel component from dp dt, since we know that the parallel and the perpendicular components add up to dp dt. Again, we use Newton's second law to calculate the perpendicular component of F net. Finally, to find the black hole's mass, I rearranged the law of universal gravitation so that we can solve for the black hole's mass. When we run the model, we can see that the parallel component of the force is pointing in the direction of the motion as the object speeds up, but then it points in the other way as it slows down. And the perpendicular component is always pointing towards the black hole, but it increases as it gets closer to the black. We also see the mass of the black hole is 2.388 times 10 to the 31st kilograms. Now, moving on to the what does it mean question. Although the value of F net and its parallel and perpendicular components are equal to delta p over delta t and its parallel and perpendicular components respectively, what the values actually mean are two different things. F net is the measure of the force acting on the system, which is causing the motion of the system, which is measured in delta p over delta t. Now, what if the black hole in this situation were replaced by another black hole, but the motion data remained completely unchanged? Then there would be no difference in our calculation of its mass. We can justify this by first using the momentum principle to state that if all motion were unchanged, then the net force wouldn't change either. Next, we look at the law of gravitation and see that as long as the total net force, the g constant, the mass of the star, and the positioning of the star in the black hole don't change, then we can conclude that the mass of the black hole will also not change.